Hello Chem 1A, this is Chapter 3, Lecture Video 5, and we're going to be discussing acids and bases, particularly the definitions of them, what they are, and how to name them. Specifically, acids is what we're primarily going to focus on here. There are actually three different definitions for what is an acid or a base, and we're only going to go over two. If you have to take Chem 1B, you'll learn the third one there. The first one is the one that we use primarily in Chem 1A way more than any other, and that is the Arrhenius definition. And this defines an acid as a substance that when we dissolve it in water, it increases the amount of hydrogen ions in the water. In other words, concentration here, we can use that word instead of amount if you want, but primarily we just need to know that an Arrhenius acid, when we add it to water, is going to increase H plus in the solution. So in other words, an acid's going to have to contain, according to the Arrhenius definition, hydrogen ions in order to increase hydrogen ions when we add it to something. An Arrhenius base is a substance that, when we add it to water, will increase the amount of hydroxide ions. Hydroxide being OH minus, right? So if we add a base to water, it will increase OH minus in that solution. So sodium hydroxide, NaOH, anything that contains hydroxide ion counts as an Arrhenius base. The second definition that we're going to go over that we probably won't use very much until you hit Chem 1B, Chem 1B uses this definition all the time, is the Bronsted-Lowry definition for acid bases. And it states that an acid is a proton donor and a base is a proton acceptor. And really, an acid-base reaction is just the transfer of a proton. Now, what do we mean by proton donor? Well, if you think about a hydrogen atom, hydrogen 1 atom contains 1 proton and 1 electron. But if we look at H+, well, we lost that electron. So H+ is really the same thing as just saying, hey, this is a proton. So that's where that vocabulary comes from. We can replace the word proton with hydrogen ion. So a Bronsted-Lowry acid is just a hydrogen ion donor. And a Bronsted-Lowry base is a hydrogen ion acceptor. And really what we're doing in an acid-base reaction is handing off a hydrogen ion from one thing, the acid, to another, the base. So those are the definitions. Now let's talk about how to name acids. We're not going to really talk about naming bases because they're pretty much ionic compounds, so we already know how to name salts that contain OH minus. Just follow your ionic compound naming. But acids have their own specific naming system. All acids contain hydrogen as the first part of their formula. So like HCl, this is an Arrhenius acid. It contains hydrogen. It increases H plus present in the solution if I add it to the solution of water. Since all of our acids contain this first bit, this hydrogen, we really don't care about it when we're naming. What we want to focus on is the anion in the acid's formula. So if the anion ends in IDE, we have rules for what we do in that scenario. We replace IDE with IC, and we add the prefix hydro to the name of the anion. So we take the name of the anion like this. This is chloride. And since it ends in IDE, I'm going to follow this rule, which means I'm going to add hydro in front of it. I'm going to take IDE and replace it with IC, so chloride becomes chloric. And then lastly, I'm going to add the word acid to the name. So this is hydrochloric acid, or HCl. If the anion ends in ATE, for example, H2SO4, we have a rule here. It's different from the previous one. The only time we ever use the prefix hydro is for our anions that end in IDE. All the other acids do not use it. They just change one thing. So in this case, I change ATE to IC if my anion ends in ATE. Sulfate, SO42- ends in ATE. So we know this guy is sulfate. And I use this as an example because it actually is a little bit of an exception to the norm. Normally, you just replace ATE with IC and call it a day, add the word acid. With sulfate and phosphate, we actually have to add some of their name back in. So sulfate becomes sulfuric. So we add UR back in and then add IC, acid. Another example might be HNO3. This is nitrate. In this case, we just take the ATE, change it to IC. This would become nitric acid. Looks like an X. Sorry, that's a T. Nitric acid. So, if the anion ends in ITE, we replace it with OUS and then add the word acid. All of our acid names are going to have acid in the name. So if we look at sulfite, again, we're going to replace the UR back into sulfite. So it's going to go from sulfite to sulfurous. And then we add the word acid. Or if we were talking about like HNO2, this is nitrite. We'd lose ITE, add OUS. So nitrite becomes nitrous, and then acid. Okay, so let's do some practice. We're going to name the following acids, right? So this polyatomic, we need to know what its name is first. This is acetate. And since it's an acid, we're going to take ATE, we're going to replace it with IC. So acetate becomes acetic acid. ClO minus is hypochlorite. Ends in ITE, we replace with OUS. This becomes hypochlorous acid. Here we have hydrogen attached to bromate, right? So this is bromate. ATE ending, we add IC. This is bromic acid. We have H2S. This is sulfide. Because it ends in IDE, we have to add hydro and IC, giving us hydrosulfuric acid. CN also ends in IDE. This is cyanide. So same thing. We have to add hydro and IC to the ending. So this is hydrocyanic acid. Writing acid formulas from the name is pretty difficult because you really have to understand the rules and where these endings and prefixes come from, right? So if we're looking at this, I have this IC here. There is no hydro, so this must have been carbonate. And if it's carbonate, then I know it's CO3 is present. And for acids, we always have hydrogen as the cation. So these two have to come together. This gives us H2CO3. Aqueous is carbonic acid. For hydrobromic acid, this must mean that we ended in IDE, or in other words, this is bromide, which means Br minus. So H plus Br minus gives me HBr aqueous. Ic, again, no hydro. This must have been phosphate, which means PO4 3 minus. So H plus and PO4 3 minus come together to give me H3PO4 aqueous. We always have to use the aqueous symbol when we're naming an acid. Iodous acid, this OUS tells me that this was originally iodite, which we know is IO2 minus. And H plus IO2 minus gives me HiO2 aqueous. Per-bromic acid tells me this was per-bromate. ATE from the IC part. Per-bromate is BrO4 minus. So we have H plus, we have BrO4 minus here. They come together to give me HBrO4 and then aqueous. All right, so we're going to talk about one more naming system here before we end this video, and that is hydrates. So what is a hydrate? A hydrate is an ionic compound. So here's our ionic compound bit, attached with water attached to it. So we have water bound to it. Now, usually there are an integer number of waters. That's this N value. It has to be a whole number. Integer. And when we name it, we name the salt first, and then we deal with the water bit. So let's talk about how we name these compounds. We write the salt name first, or the ionic compound name first. And then when it's a hydrate, we add the prefix for however many N was in the previous formula, right? How many waters are attached to my hydrated ionic compound? We're going to use our Greek prefixes here to indicate how many waters are attached to it. And then we write the word hydrate. So for instance, prefixes could be mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, so on. So if we look at this compound, it's a hydrate. We have a water attached. There's always this like multiplication dot to indicate the water's bound to the ionic compound. So if we're naming the ionic compound first, we just write barium, right? And then this is chloride, so barium chloride. Next, we have to add this bit here, the prefix plus the word hydrate. Since there are two waters, this is going to be the prefix di, so dihydrate. Our full name of this compound would be barium chloride dihydrate. All right, let's go the other direction. So if I have sodium sulfate pentahydrate, then what I need to do here is first write my ionic compounds formula. I know sodium is Na+, sulfate is SO4 2 minus, so I got to create my ionic compound there. That would be Na2SO4. Then I'm going to do my multiplication dot. Pentahydrate, penta is the prefix for 5, so I'm going to write 5, and then H2O. And so this is my formula of sodium sulfate pentahydrate. All right, so now we're done learning how to name things, at least for the time being. We do have organic compound naming, tiny bit of that, which is just straight up memorization at that point. And you'll learn a lot more about that in the next Chem 1, in Chem 1B and organic chemistry if you have to take those classes. All right, as always, if you have any questions, please don't hesitate to contact me.